Hello. Okay. Are we all right? Very good. Okay. I was muted for a while. Oh, I see the chat now. Okay. I was muted for a while, but now I'm good. All right. So let's go. Let's get started then. Thank you. And thanks everyone for the flexibility meeting at unusual time today. Yeah. I think yeah, a few meetings ago, we saw the sum check protocol. Last time we saw some applications of it. I think we did counting triangles and matrix multiplication. Um, so those were sort of special purpose applications, using the SymCheck protocol to solve specific problems, to force the prover to do the hard work of solving the problem. The verifier essentially just reads the input to the problem. Um, but now today we're going to see how to use the SymCheck protocol to get what I would call a general purpose interactive proof. In the sense that, so it's an interactive proof for a problem called circuit evaluation. And in principle, like any computation can be turned into an instance of circuit evaluation. Um, and so by giving an interactive proof for circuit evaluation, you're sort of thereby giving an interactive proof for anything. Okay, but we'll be talking a lot more about the intricacies of how one turns general computations into circuit evaluation instances. And there are a bunch of caveats regarding, like, some computations, if you're not careful, the equivalent circuit is enormous, maybe I just, so snarks in general, they typically at least if you want to be able to prove statements about arbitrary computer programs, which I call general purpose snarks, they sort of have two components, like a front end and a back end. Okay, and by front end, what I mean is something that will take some high level description of what's being proven, say like a computer program, like a Rust program, which takes as input like a witness, and the prover is claiming to have like correctly run the Rust program on some witness to produce some claimed output. And what the front end will do is it will turn the Rust program into a circuit. And so we'll see, today, like, what is a circuit, but like, so it turns it into the computer program. So witness W, into an equivalent circuit. I think I maybe drawing my circuit like upside down, but whatever. Okay, and so that's what the front end does. It gives you the circuit, right? And then what the back end will do is the back end of the snark is like a proof system to prove the prover correctly evaluated the circuit. Okay, and so today we're focused on the back end. Okay. But there's a lot to talk about regarding like the front end as well. So today we're just going to assume we have a circuit and the prover's claiming it evaluated the circuit correctly, and we're going to talk about how it can really efficiently produce that proof. And even within the back end, there's a lot we're not really going to discuss today, because here I'm going to assume today that like the verifier is just going to know the W. Okay, but in snarks, especially if there's zero knowledge, but also if you just want them to be succinct, yeah, in order to it better be the case that the verifier does not learn W, right? That would violate zero knowledge, and that would also violate succinctness. So in SNARKs, we'd want the verifier, not to know W. Instead, like the prover will wind up cryptographically committing to W. Okay, and I'm just going to ignore that sort of thing today for the most part. Okay, so here's the setting for today. Okay, so the prover and verifier, like in advance, like before anyone necessarily even knows W, the input to the circuit, they agree on a circuit. And I'll explain again what a circuit is, but specifically an arithmetic circuit of Fanon 2. Okay, so let me explain what that is. I don't expect you to know what that is right now. An arithmetic circuit consists of gates and edges. Okay, and it's so gates and let's say wires. So it's easiest to see with an example. So what the gates do, they compute addition and multiplication over some finite field. Call it F. And so you have your inputs. Let's say the inputs are field elements. So let's say that so each of these is a field element. So W1's in the field, W2's in the field, W3's in the field, W4's in the field. Right. These are the inputs to the circuit. And then what the circuit will do is it'll just add some inputs together, multiply some inputs together, and then take the results of those operations and feed them into additional operations. So maybe those things, and that eventually produce some output. So this is a little circuit. This is an arithmetic circuit of Fanon 2. It has 4 inputs. 3, I call them interior gates. Non-input gates. These 3 gates here, and it produces 1 output. Okay, so I say this is just my personal terminology. I call the sum of these 2 things the size of the circuit. So I consider the inputs to be I call them input gates. I think most people call them input wires. I call them input gates. And then, and then the size of the circuit is just the number of gates in the circuit, and I count the inputs towards that. So that's what we mean by size of the circuit, number of gates in the circuit, including the inputs. So just, to make this really concrete, let's evaluate the circuit on a particular input. Okay, so let's say the first input is like the field element 8. The second input is, 1, 3, and 1. So, this gate here adds, the first 2 inputs together. So the value of that gate on this input is 9, right? Because 8 plus 1 is 9. And this gate multiplies, these 2 inputs together. So the value of this gate on this input is 3. And then this gate multiplies, these 2 values together. So the value of this gate is 27, and that's the output of the circuit, 27. Okay. And so what Fanon 2 means is just that every gate in the circuit is fed at most 2 wires. Right. So, by that, so like this gate, it's these arrows are called the wires for that gate. Right. So, this addition gate, takes these 2 inputs as input to the addition operation and sums them. Yeah. So, Fanon 2 just means we're summing up only 2 numbers at a time. Fanon 2 means we're multiplying at most 2 numbers at a time. So that's what Fanon refers to. Like how many values does any gate act on? Okay, so that's a circuit. All right. And let me just pause here and see if anyone wants to ask any questions about what an arithmetic circuit of Phanon 2 is.
Hello, Professor. I just had a quick question. So you are assuming some depth bound for these circuits that you're considering, right?
Yeah, so with the cost of the protocol we're going to see today will grow with the depth. So you can apply the protocol in general, no matter how deep the circuit is, but like it's not going to be a very interesting protocol if the circuit's super, super deep compared to, its width.
So is there a concrete value of the depth that you are assuming in your setup?
No. The one thing I will assume that technically I didn't introduce yet, although my picture sort of had it baked in, is I'll be assuming the circuit's layered. Which means like you can sort of break the gates into layers so that the gates at layer I, are connected to gates at layer I minus one. And so basically, like if I had an arrow from like the input layer straight to the output layer here, that would not be layered. But yeah, this is layered because like the inputs are just connected to only these two gates, and then these two gates are connected to the next gate, and there's there's no arrows kind of jumping ahead multiple layers. But yeah, there I'm going to basically what the GKR protocol is going to do is that for each layer of the circuit, the sum check protocol is going to get invoked. So, if there are 10 layers of the circuit, you invoke the sum check protocol 10 times. And so, if there are 100 layers, you invoke it 100 times. And so the proof size is just getting bigger and bigger the more layers there are. So like the protocol works for any number of layers, but like, if you had a circuit that was like one gate per layer or something, this is a circuit that just, takes its input and squares it over and over again. And that was your whole circuit. Well, then this the proof today will be bigger than the size of the circuit, and that's just like very silly. At that point, like the verifier, will spend more time reading the proof than just if it had done the computation on its own. But the protocol still works. It's just a giant proof. Does that make sense?
Yes, sir.
Yeah. Thanks for the question. Other questions? Okay. All right, so yeah, let's do it. So in order to, maybe I'll give a very, very high level overview of the protocol, and then I'll have to introduce some slightly annoying notation. But once you have the notation out of the way, it's a pretty quick protocol to describe. Okay, so very high level, what we're going to do is the following. So, okay, this example here I'm going to use. It's deceptively small. It's a little bit annoying. Actually, okay, yeah. Let's stick with this example. So the prover is going to send the claimed output to the verifier. 27. Remember that the verifier knows the inputs and knows the claimed output. And now the prover needs to prove that indeed this claimed output equals the value of the output gate when the gate is evaluated, when the circuit's evaluated on the input. And so what's going to happen is the prover and verifier will run the sum check protocol. Okay, and that will sort of reduce the prover's claim about the output to a claim about the layer of gates feeding into the output. Okay, in the sense that if the claim the prover makes about this layer is true, then it's somehow safe for the verifier to believe that the claimed output was also correct. Okay, so from the verifier's perspective, we run the sum check protocol once, and it's a reduction that reduces, the checking the original claim about the output to checking a claim about the layer feeding into the output, right? So we made some progress, right? Like the output is like the furthest gate from the inputs. And now we're a little bit closer to the inputs than we were before. Okay, but we haven't made that much progress, right? Because like evaluating the gates feeding into the output is like almost as hard as just evaluating the output itself, right? Because once you know like the value of these gates or something, like it only takes one more operation to compute the output. right? So we're not done, right? Like the verifier can't actually check this claim here that it's left with after that first sum check protocol. But fortunately, it turns out like the claim that the prover makes about these gates sort of is a very similar form to the original claim. Okay, and I'll elaborate on this in a bit. So you can actually just apply the sum check protocol again. Okay, and that will reduce this claim about the layer of gates feeding into the output to an equivalent claim about the gates at the preceding layer to that. Okay, so in this way, like every time we call the sum check protocol, we sort of move one layer closer to the inputs. Okay, and eventually we actually force the prover to make a claim about the inputs themselves, which in this example, is you only apply sum check twice and you're there. But that's just because this circuit is such a simple toy. If you had more layers, it would take more applications of sum check to get to the input. And the verifier, once you get to the input, can actually check the claim that the prover makes about the input in linear time and the size of the input. So like order n time, where n is the size of the input. So if the input is called W, here the input is in field to the n. It's n field elements. Okay, and that's what we wanted. Yeah. So because the verifier has to at least read the input to have any idea what statement the prover is even making. You can't hope for the verifier to run in time sublinear in the size of the input. So yeah, this is that's what happens in the GKR protocol. And so it's a way to offload the hard work of evaluating the circuit to the prover. So, imagine it's not very interesting in this little toy example where the input is like more than half of the gates in the circuit. But, there's lots of situations where, the circuit will be much bigger than the input. And so, the verifier in that case would be saving a bunch of time, because rather than having to evaluate the circuit gate by gate, it just has to read the input, and the input's much smaller than the number of gates in the circuit. Okay, and then in snark land, there's also the situation that often, as I mentioned before, and so I brush under the rug today, often the verifier does not know W. Often in snark land, W will be committed. Okay, and then it turns out the verifier, can check the claim about W, the input, in sublinear time in that case. So it depends on the commitment scheme you use, but some of them will take square root n time, some of them will take log time, some of them will take constant time. And so that's another thing where you actually in snarks you often do apply the GKR protocol to linear size circuits. It's still useful for the verifier, basically because in that case, the verifier doesn't even need to read the input. The input is committed, and the commitment scheme comes with a way to let the verifier check the prover's claim about the input really, really quickly, in sublinear in the size of the input time. Okay, but yeah, today, to brush that under the rug, let's just imagine the circuit is, size n squared and the input is size n. And so this is a way to make the prover do the n squared work of evaluating the circuit, and the verifier just does, just basically reads the input. That's order n work. So yeah, now because we applied the sum check protocol once per layer of the circuit, the total proof size is so it's depth of the circuit, so number of layers, okay, times like log, like circuit, like log of the circuit width or whatever. Let's just say log size of the circuit. Okay, and what's going on is every time you apply the sum check protocol, it winds up having proof size that's like log the size of a particular layer of the circuit. Okay, and you apply the sum check protocol once per layer. So the total proof size is number of layers times log like size of each layer. So is that size of circuit is actually sort of an overestimate. It's really size of each layer or size of the biggest layer or something like that. And so, often the depth of the circuit is like logarithmic in the circuit size. And so in this case, the proof size of the GKR protocol is log squared of like circuit size or input size or whatever. Okay, so concretely, like Jolt, it uses the GKR protocol a bunch, and concretely, the proof size can be, if we did pure GKR, it'd be a little bit bigger. Let's say 50 kilobytes to 100 kilobytes, depending on exactly how big your statement is or something. And so it's not the smallest proofs, but for comparison, like the Frye polynomial commitment scheme, proof size is 100 kilobytes and more typically, at least if you're typically asymptotically, it's like security parameter times log squared of like the size of whatever object you're dealing with. And so this is actually bigger than GKR by this order security parameter. My point being that GKR proofs, they're not tiny, but they're also smaller than some of the other popular protocols today. So just sort of giving you a ballpark. Much bigger than KZG proofs, but smaller than Frye proofs, something like that. Okay, and so let me just pause there. That's a high level overview of how the protocol works. I'll give you just a little bit more detail, but let me see if anyone wants to ask any more questions. No? Okay. Well, feel free to interrupt me at any time. So let me give you a little more detail about what these claims are. So you start with a claim about the output gate. And when you apply some check, that gets reduced to a claim about the gates feeding into the output. So more precisely, what is that claim? Okay, so what we're going to do is we're going to consider the multilinear extension of the vector of gates at each layer. So let's call this, I forget, I don't have the book in front of me. I'm guessing in the book, I probably called the multilinear extension of this layer. I'm guessing I called it like V1 twiddle. This one would be, well, let's just forget the output later. And this would be V2 twiddle. And so, what the claim that the prover winds up making about this layer, the layer feeding into the output, is it winds up claiming that V1 twiddle of R equals some value. Let me call it Y, where this R is random, a random input. Okay, so the claim is not. Whenever I describe this protocol, people ask, what is the prover just sending like 9 and 3 to the verifier? Is that all? It is just literally sending the whole layer to the verifier, and the answer is no. And instead, it winds up sending it like making a claim about a single value. A single evaluation of the multilinear extension. And so then a follow-up, natural follow-up question is to think, like a random input to the multilinear extension, well, that must be the same as picking a random gate in this layer, right? And, like a natural thing to try, but it doesn't work, is to say, hey, like I'm going to, okay, so here's a straw man that doesn't work. So let's say the prover actually did send 9 and 3 to the verifier, okay, and the verifier checked that 9 times 3 equals 27, and so great, like now the verifier actually knows this whole layer, and then you could think, well, let me just pick at random 9 or 3 and sort of just check that the thing I pick was computed correctly. So let's say I randomly pick 3 rather than 9, and then I make the prover send me 3 and 1, and I confirm that 3 times 1 is 3, and so I check that this gate was computed correctly, and now I'm good. And that that doesn't work. So the high level idea here was, which doesn't work, is to sort of at each layer once if the prover has told you the value of 2 gates at that layer, pick one of the 2 values at random and make sure that one of the 2 values was computed correctly. Okay, and so you do that once per layer, and like you get similar costs where the proof size would be two values sent per layer. Here it's with the actual GKR protocol, it's logarithmically value sent per layer, but 2 and log are not that different. The problem is the soundness error, right? So like if one of these 2 values is wrong, you only have a probability 1/2 of picking the wrong value. We're not happy with soundness error 1/2, and most likely, with this straw man approach, I think that the actual you're only going to catch the prover in a lie with probability like 1/2 to the depth chance of catching a cheating prover, which is terrible. So so that's a straw man to have in mind, and the GKR protocol is like a little bit related to that, but it's not that. And why is it not that? The key point is that this random input at each level, it's random from the whole field, right? So picking a random gate at that level is that the GKR protocol will wind up assigning each gate a binary label. This gate here would be assigned label 0 at this layer, and this gate here would be assigned label 1 at this layer. And similarly, this input gate would have label 0 0, and this one 0 1, and this one 1 0, and this one 1 1. And so picking a random gate at each layer is like picking a random element of the hypercube. But the randomness here is from the whole field. Okay, and that's why the GKR protocol winds up having good soundness error, while this straw man, where you just kind of pick a random gate at each layer, has very poor soundness error. Okay, so just a little bit of extra color about what actual claim does the prover make about each layer. The claim winds up being a claim about a single evaluation of the multilinear extension polynomial of each layer. Okay, so just to redraw the example again real quickly. So I think this was the circuit. Okay, so here were our functions. So the vector of gates at this layer, we wind up interpreting this. So this is layer 1, this is layer 2. And so the gate values at this layer being, the 0th gate at this layer having value 9, and the first gate having value 3, that we interpret as a function. So v1 of 0 is 9, and v1 of 1 is 3. Okay, and similarly with this layer, we interpret the gate values of this layer as a function. v2 of 0, 0 is 8. v2 of 0, 1 is 1. v2 of 1, 0 is 3, and v2 of 1, 1 is 1. Okay, and so these are what I call the gate value functions. For each layer. So this is the gate value function for layer 1. This is the gate value function for layer 2. So all I've done is I've taken the vector of gate values at each layer, and as we've discussed, over the last few weeks, there's a little song and dance you do to be able to talk about the multilinear extension of those functions. And so, because each of these functions has domain equal to the Boolean hypercube, we can take its multilinear extension polynomials. And so, like, if I actually I visualize things as follows. So if you look at, if you that while V1 has domain 0, 1, because there's two gates at that layer, V1 twiddle has domain the whole field. Okay, which means if you visualize like the evaluation table of V1 twiddle, it's a huge vector, one entry per field element. And so, I can actually tell you what V1 twiddle is. V1 twiddle of x is 9 minus 3x. It's the unique line that maps 0 to 9 and 1 to 3. And so, I can evaluate V1 twiddle outside of the hypercube at any field element. So I can evaluate it at, V1 twiddle of 2 would be, sorry, did I mess this? Sorry, 9 minus 6x. So V1 twiddle of 2 would be like minus 3, and V1 twiddle of 3 would be minus 9. V1 twiddle of 4 would be minus 15, and so forth. Right. And similarly, there's some, the domain of V2 twiddle is field by field, because V2 twiddle is a bivariate polynomial. And so the way I visualize what's happening in the GKR protocol is, the first invocation of the sum check protocol reduces the prover's claim about the output gate of the circuit to a claim about like a random entry of V1 twiddle. So the claim is that V1 twiddle of R for some randomly chosen R equals some value. And so let's say this is the rth entry here of this, evaluation vector of V1 twiddle. So I reduce a claim about the output gate to a claim about like one random evaluation of V1 twiddle. I then apply sum check again, which reduces the claim about one random entry of V1 twiddle to one random entry of V2 twiddle. And if I'm not in this example, I'm now at the input layer, and the verifier can evaluate V2 twiddle if this is the input layer, with via multilinear Lagrange interpolation in linear time, and we're done. Okay, so that's what's going on. That's kind of full detail of how the GKR protocol works. Just I now need to still tell you what polynomial the sum check protocol actually gets applied to at each layer. But again, the point of the first invocation of the sum check protocol is to reduce the claim about the claimed output to a claim about a random evaluation of the MLE of the gates at the preceding layer. And then we apply sum check again to reduce that claim to a claim about a random evaluation of the MLE of the gates at the preceding layer. And, we just move one layer at a time closer to the input. And then finally, when the verifier makes a claim about a random evaluation of the MLE of the input, well, the verifier can check that claim on its own via multilinear Lagrange interpolation. Okay, let me pause again and see if anyone wants to ask any questions now.
There are some questions in the chat, although it's not clear there for you. The first one says the MLE helps with the sum check protocol, and then you extend it to the hold field for soundness, since you can send a degree 1 polynomial at each round.
Well, I think in the GKR protocol, you'll actually send a degree 2 or 3 polynomial in each round. But what's going on intuitively is the MLE helps for soundness because of like the distance amplification properties of low degree polynomials, right? So it's just the usual thing intuitively where if I'm at a layer and even one gate value at that layer is wrong, then like the MLE of that layer actually differs almost everywhere from the MLE of like the real layer of like the real vector. And so that's the property you want, that the kind of the straw man I sketched before didn't have. This property that if the prover sort of messed with even a single gate at that layer, that some object that the verifier is ultimately dealing with actually has a very easily detectable deviation from truthfulness. So that's why the MLEs come in for good soundness, kind of turning even a single error at each layer into some giant easily detectable situation. But then the sum check protocol for the prover is also really fast. It's all field additions and multiplications that the sum check prover does. There's no cryptography. As I'll discuss if I don't run out of time, actually the prover work in the GKR protocol is order circuit size, which is sort of amazing because it takes circuit size field ops just to evaluate the circuit. Right. So basically the prover's claiming, hey, I evaluated the circuit gate by gate and, on this input, and it produced this output. Okay. And the verifier's like, I don't believe you, prove it to me. And the prover's like, okay, like, here's the proof. And computing the proof is only a constant factor slower than what it took to like compute the output anyway. And in fact, I think this hidden constant now we probably have down to something like, I don't know, 10 or something, 10 times circuit size. It might even be 5, but I think it's 10 field ops to compute the proof. Right. So, this prover is still, an order of magnitude slower than what's required to, evaluate the circuit, but it's only one order of magnitude, right? Like most snarks, like Jolt, when initially released, the Jolt prover it's getting faster now, but was like 500,000 times slower than just running the computer program it claimed to ran. So like a 10x slowdown, compared to a 500,000 fold slowdown is like nothing. And so the GKR protocol is like just one component of Jolt. So like there are other slowdowns coming in, but if the Jolt prover is like almost 6 orders of magnitude slower than just computing the right answer, only one of those 6 orders of magnitude at most is coming from GKR. All of the other 5 orders of magnitude have to be coming from some other part of the protocol. So was that a little bit helpful?
The person who asked has not chimed in, but Scott, did you have a question? You hopped on stage.
Yes. I had a discrepancy in connection, so maybe I just missed the answer. But I was trying to understand why does GKR requires few uh, requires requires an multilinear extension for each layer and not just enumerate each gate one by one. I vaguely remember a recording of your lecture where you present a protocol. I don't remember which one, where it just runs over all gates enumerating like this, and if I remember correctly, using one extension. And I was trying to understand if it if it if it related to lowering the total degree of the resulting polynomial.
Yeah, it's a great question. You probably saw me talking about Spartan, and so here's the answer. In something like Spartan, really in any snark that is not GKR based, the very first thing the prover will do is it'll do exactly what you said. It will look at the multilinear extension of the whole circuit, everything, and it will cryptographically commit to it. Okay, that's the very first thing the prover does. Okay, and then once the whole thing is committed, it only takes one or at most two sum checks to kind of finish off the problem. The reason the GKR protocol needs to take a different multilinear extension for each layer is to avoid committing to the interior gates of the circuit. Or if the verifier knows the input, then in the GKR protocol, there's no commitment to anything at all. So that's why. So it's like somehow the sum check protocol, like in Spartan, reduces the prover's claim about the output gate to a claim about one evaluation of the MLE of the whole circuit. Okay, but like without any cryptography, without the whole circuit having been committed, that reduction is not useful. Like evaluating the MLE of the whole circuit is like not any easier for the verifier than just evaluating the whole circuit. It turns out to be useful if the whole circuit has been committed, but not otherwise. So in the GKR protocol, we want to avoid the whole circuit needing to be committed. You know, because either originally it was just because GKR were interested in an interactive proof, and like, you know, so they didn't want to use any cryptography just for like theory reasons. But in practice, it turns out to be interesting because cryptography is expensive. So committing to the whole circuit can be expensive. So here, you know, the prover just does field work proportional to the size of the whole circuit, but does not commit to anything at all. Does that help?
That makes sense. So we just kind of exchange a huge commitment for few tiny commitments to only inputs and output.
Right. Yeah, that's pretty much. And in fact, if the verifier knows the whole input, then the whole input doesn't even need to be committed, and then there's really no commitments anywhere. And yeah, the cost is that like Spartan has logarithmic size proofs, log of circuit size, you know, plus you know, any polynomial evaluation proof from the polynomial commitment scheme that's used. Whereas GKR has depth times log circuit size proofs. So you get you know, the proofs are a little bit bigger for GKR, but they're still small enough that I think it's fine, you know, totally fine. But yeah, that's the cost. So it's like, you know, faster prover, bigger proofs. That's the trade-off. It's a common tension in snark design. Often verifier cost and prover cost, you know, you sort of trade off one for the other.
That's a lot of content that puts it in the context. Very nice. Thanks a lot.
Yeah. Thanks for the question. Okay. Other questions? All right. Okay. So I was introducing some notation. So we're sort of partway there. So I've introduced, you know, the multilinear extension of the gate values at each layer. Okay, I need to introduce two more functions. Okay, let me just erase this stuff about the jolt prover speed and GKR prover speed. Yep, go ahead.
May I ask you a question before we move on? So does this like layer by layer in JKR, does it help with parallelization as well, or that's a separate? Because I hear like JKR is used in some like products that they claim that this helps with parallelizing the proof generation.
Interesting. I'd actually think it's more of the opposite. It sort of feels like a sequential bottleneck a little bit. Not that I actually think it's a, you know, major one, but just because you can't start proving the claim about layer I plus one until you're done computing the claim about layer I, because you don't know what claim about layer I plus one you're going to be left with until you finish proving, like running some check for layer I. So that actually feels like a sequential bottleneck. But there's other very nice things about GKR. There's no FFTs. There's no quotient polynomials, which can be like a major bottleneck to compute over. Sum check is like very parallelizable itself. But if you're running, like 100 sum checks, one after the next, that actually feels like that should be a sequential bottleneck, not something good for parallelization necessarily. But what do you think? Does that make
Okay.
Would it make any sense to commit to each layer, like rounds, and it would be much smaller still than Spartan way?
I think what really matters in the end is just how much data gets committed in aggregate for the most part. So I don't think it's really any better to like commit separately to each layer than to commit to all the layers all at once. There are some caveats to this about, polynomial evaluation proof computing can be a bottleneck for the prover for some polynomial commitment schemes. And so if you commit to each layer separately, you can batch the evaluation proofs, whereas if you commit to them all at once, you can't. But anyway, without getting into those details, I think it's roughly the same whether you commit to all the layers at once or commit to each one separately. It just matters how much data you commit to in total. And with the GKR protocol, it's at the very, very extreme in terms of minimizing the amount of data committed to, in some settings, there's just literally no commitments whatsoever. Yeah, I don't know. I mean, coming back to the parallelization question, I mean, the fact that you sort of prove each layer separately might be good because, the amount of data the prover needs access to at any given time is smaller. So maybe the data fits in cache better or something. But yeah, I mean, generally, I think the GKR protocol is great, and I advocate for its use. But I don't think the layer by layer thing is like good for parallelization in and of itself.
Great. Yeah. Thank you.
Right. Other questions?
Yeah. One more question.
Mm.
In like the Lasso code base,
Mm.
I might sound like I'm going off topic, but I think it relates to the GKR protocol. There's like a memory checking proof
Mm-hmm.
that inside of it has like a product layer proof, which
Mm-hmm.
obviously makes sense with GKR. But then after that, there's like a hash layer proof. So I was wondering what that is, if you know, or if
Oh,
it's not
okay, yeah.
related.
So I think hash might be a little bit confusing there, but what's going on is in Lasso, I'll keep this short since I guess it is slightly off topic, but it is nice to talk about like an application of GKR and like, in snarks, like how is GKR actually used. So the lookup argument in Lasso is a lookup argument. Like what you wind up with is a bunch of 3 tuples. So triples of field elements. So A1, V1, T1, up to AN, VN, TN. And I guess you really wind up with like kind of 2 lists of triples. So A1 prime, V1 prime, T1 prime, up to AN prime, VN prime, TN prime. Okay, and then the big question is, like, let's call this list A and let's call this list B. And the big question is list A permutation of list B? Okay, it turns out that like, the prover's claim in the lookup argument was correct if and only if list A is a permutation of list B, right? So let's just take that for granted. There's not going to go into the details of that. And so what we do is the following. So it's a little annoying that these are triples of field elements, right? We kind of want to reduce each triple of field element down to a single field element. And so what we do is we replace, so it's sort of a 2-step process, replace each triple with a single field element. Okay, and that's probably what you saw as the hashing layer. At least I hope, because if not, I'm a little confused. But also, we shouldn't spend more time on this since I can't stay very long after the hour today. And so, this is done via what's called fingerprinting. Some people call it hashing, but anyway, and so that will replace AVT with the verifier picks a random gamma or something and replaces AVT with like something like A plus V times gamma plus T times gamma squared. And this is sort of as long as the prover committed to all these triples before it learns what gamma is, this is very unlikely to introduce a collision. So different triples should map to different fingerprints. Call this the fingerprint of AVT. And that's what we want. So now assuming there were no collisions, the question of whether list A is a permutation of list B is equivalent to the question of, is the fingerprints of list A a permutation of the fingerprints of list B? And that turns into a grand product. So, we want to know, is, like fingerprint of A1, V1, T1, fingerprint of AN, VN, TN, a permutation. So this is like a big vector now, big list, whatever you want to call it, of this other big list, finger A1 prime, V1 prime, T1 prime, up to finger A1, AN prime, VN prime, TN prime. And we've discussed permutation checking before. You basically wind up interpreting each of these things as the root of a polynomial and evaluate that polynomial at a random point. And so that what turns into a grand product. Okay, so what we wind up applying GKR to is the circuit, which is just a binary tree of multiplication gates that multiplies all these things together, right? So what we're feeding into this circuit is sort of is these fingerprints, So the input to this there's actually two grand products. One producting all these fingerprints together, more or less, and another producting all these fingerprints together, and then you just check are the outputs the same. And so what GKR gets applied to in Lasso is just this circuit. It's just a binary tree of multiplication gates, but the inputs to the circuit are a little bit funny, right? They're these fingerprints, and ultimately these fingerprints are really committed. Yeah, so the verifier in Jolt and Lasso never actually sees these triples. They're all inside some commitment, essentially. So hopefully that's a little bit of interesting color about how GKR actually gets applied in SNARK design. But I think that's what's going on in what you saw in Lasso and Jolt.
Thanks.
Yeah.
I had a quick question, Professor. I think it was just said that the prover did MLE for every layer, but then the verifier only interpolates for the input layer.
Mm-hmm.
So would it be
That's right.
possible to add some intuitive color to what property of MLE is enabling this particular behavior?
Well, it's mainly intuitively the distance amplification, the Schwarz-Zippel thing. You take two different vectors or functions or whatever, and their ML, even if they differ in even a single entry, a single input over the hypercube, their MLEs differ almost everywhere. That's really all we're using. And then as we've discussed before, when you use multilinear polynomials within the sumcheck protocol, it can be pretty nice for the prover as well. Those are really the only two things going on that make the MLE so nice. In fact, if you go back to the original GKR paper, they did. Okay, it's interesting. So I'm probably going to not cover the whole protocol today, since not surprisingly, I'm sort of out of time, and I actually can't blow past the claimed endpoint like usual today. But so I introduced the notion of gate values at each layer. There's one function or two functions for each layer I haven't introduced yet, which basically tell you the wires of the circuit. So these functions, which I'll introduce next time, they're called add and mult, and they sort of tell you, for each addition gate or each multiplication gate, which other gates are they adding or multiplying together. Okay, and GKR in the original paper actually did not use multilinear extensions of add and malt. Okay, and as a result, their prover actually ran in time like cubic or worse in the size of the circuit. Okay, and then my work said if you use the multilinear extensions of add and malt, the prover can actually be nearly linear in the size of the circuit. And so there you're seeing a major prover benefit of using the multilinear extensions of things instead of other extensions. But yeah, so basically, you know, all you need really, you can really use any extensions and you'll get soundness, but then like non-multilinear extensions might not lead to a nice fast prover. Is that clear?
So, I think the confusion for me is stemming out of the fact that GKR protocol, the paper does not talk about MLE. So, do I understand this correctly that what you're trying to say very vaguely would be that the MLE of each layer that the prover creates actually goes on to become one MLE for the input layer?
Yeah, that's right. That's right. Like ultimately, the prover is forced to make a claim about one evaluation of the MLE of the input layer alone, and the verifier can compute that evaluation on its own in linear time via multilinear Lagrange interpolation. Now, if you look at the GKR paper, I think you won't see 0, 1 to the n anywhere. They probably talk about like h to the n, where h is just like some subset of the field. But you can always set h to be 0, 1, and in that case, I think GKR would be using, like back in their original paper, MLEs of the gate value functions. So MLEs of, you know, like V1, V2 up to the number of layers. But there are these other functions called add and malt, one per layer, you know, add one to add number of layers, or malt one to malt number of layers. And there, they did not use multilinear extensions. Okay, and as a result, their prover time, you know, claimed in that paper was like just some polynomial in circuit size. And if you look at it, if you look at it carefully, it's circuit size to the fourth, or, you know, if you're very naive about things. So yeah, but it turns out if you do use multilinear extensions, you can actually get a linear time prover. Yeah.
Thanks.
Okay. So actually, I possibly just want to wrap up here for the week, even though we didn't quite see it, but we did sort of cover all the groundwork. So like next week has to be an off week, which is really annoying. So you'll kind of lose the thread of things, unfortunately, but it's okay. So we set all the groundwork, and but I haven't actually told you like what polynomial we apply the sumcheck protocol to at each layer, you know, to reduce like a claim about, you know, an evaluation of the MLE of layer I to a claim about an evaluation of the MLE of layer I plus 1. So I will tell you those details next week, but, you know, I mean, I guess I can say a quick sentence about it. What we wind up doing is expressing the multilinear extension of layer I at a point as a big sum, and you're not going to follow the details here, but let's say you write it as a big sum of something, let's say G of R comma B comma C, where G depends on like okay, so it involves add twiddle, malt twiddle, as well as the gate values at layer I plus 1. Okay, so let me just to give you a sense of things. So let's pretend for a second that there are only multiplication gates. That's actually the case in Lasso and Jolt because we just use GKR for grand products. There's, you know, so there's only multiplications. So we would have malt like R comma B comma C times VI plus 1 twiddle of B times VI plus 1 twiddle of C. Okay, and yeah, so you know, we took a claim involving layer I, and we applied the sumcheck protocol to some polynomial, which involves only layer I+1. Okay, and what we'll see next week, the details is like, this is just capturing the fact that, if, so what this is, the reason this equality holds turns out to be like, we define malt so that, if B and C are the in neighbors of gate A, then malt of A comma B comma C equals 1, and otherwise malt of A comma B comma C equals 0. So again, I don't expect you to follow this, but and so it's very similar to multilinear Lagrange interpolation, where here you're summing over like all possible in neighbors to a gate at layer I, in neighbor pairs or whatever, to a gate at layer I, and then this malt function will just kill all of the pairs that like aren't actually the right in neighbors for that gate. But then if B and C are the right in neighbors for a given gate, then malt will output 1, and then here we have the product of those two in neighbors, which is exactly what the multiplication gate we're talking about computes. So to summarize, well, I didn't expect you to follow that at all. What we do is we express the multilinear extension for layer I as a big sum of evaluations of some polynomial, where that polynomial involves only the gates at layer I+1. Okay, so you just apply the sum check protocol to this polynomial G. At the end of the sum check protocol, the verifier has to evaluate G at a random point. That entails evaluating, VI+1 twiddle at random points. And so we have successfully reduced, the evaluation of layer I to actually it's 2 evaluations at layer I+1. Then there's a little trick you can do to reduce, the claim about 2 evaluations at layer I+1 to just 1 evaluation at layer I+1. And that's the protocol. That's how the reduction is done. And so you just go 1 layer at a time, and after D layers, you finally have a claim about 1 evaluation of the input layer, MLE, and the verifier can do that on its own in linear time with multilinear Lagrange interpolation. Okay, so hopefully you get some sense of what's going on in this protocol. Apologies for the rushness and, obviously the details you can't follow this quickly at all. So next week we'll be off. The following week I'll show you the details, and it's a pretty awesome protocol and looks like it's getting adopted more and more. So hopefully it'll be an important one moving forward too. So I'd like to wrap up here, but happy to answer questions async in the chat if anyone wants to ask. So thanks again for your flexibility. I really appreciate it. See you in 2 weeks.